Good afternoon, everyone. Good afternoon, session chair, all panelist members, and all my dear participants.
Good
I
afternoon.
would request session chair to please start the session.
Thank you, Subnil. Good afternoon, everybody. And I welcome you all to this session one for this power plant summit. And I think, as we know, the demand for electricity and heat production is largely covered by conventional thermal power plants based on fossil fuel combustion. At the same time, the thermal power stations face a big challenge to meet the environmental requirements, constantly keeping process efficiency and avoiding lifetime shortening of the critical components. In recent years, many activities have been observed to reduce pollutant emissions, optimize performance in thermal power plants, increased share of renewable sources of energy in domestic market, and forcing flexible operation and fast adjustment to actual demand. Operation under changing load together with keeping emissions at the accurate levels require constantly introducing new solutions and technologies, as well as carrying out many research and development activities for optimization of the electricity and heat production process. In this session of Power Plant Summit is aimed to present the advancements in ultra supercritical boilers, new technologies, innovative solutions, tools and computational methods dedicated to thermal power plants in the light of new trends and challenges. So that is in brief is the some sort of scenario which is prevailing, and taking this opportunity, now I request Mr. Chinna Rao Kotagiri, who is the Vice President, Head Engineering of L&T MHPS Boiler Private Limited. He is having about 35 years of experience in engineering area of the power plants. So I invite him for presenting a paper on this latest advancements on ultra supercritical boilers. Mr. Chinna Rao Kotagiri.
Yeah. Thank you very much, Mr. Agarwal, for the introduction. And in this session, I am going to have of course, whether I call it advancements in ultra supercritical or not, I am not sure. But yes, the ultra supercritical boiler, the first ultra supercritical boiler which we have supplied in India, which has gone into operation. I just talk about that particular unit and what are the design improvements compared to the supercritical to ultra supercritical? What are the additional features which has to be incorporated? Those things also I am going to discuss a little bit. Because the time is only 15 to 20 minutes I have to cover. So I will start my presentation. Everybody is able to see the full slide mode?
Yes, sir. It's visible.
Okay. Yeah. Of course, before I just go into the technical this thing, because maybe some of the people may not be knowing our company because it is L&T MHPS boilers. I just briefly 2 slides I will show you what is that we are doing, what is our company. Sorry, it's not moving. Next slide has come or no?
No, sir.
Now it has come, okay.
Now it has come, yes.
Yeah. This is a joint venture company between L&T and MHPS. L&T has 51% stake and MHPS has 49% stake. We call this company is L&T MHPS Boilers. In short term, we call it LMB. This joint venture has been incorporated in 2007. The complete technology transfer for the supercritical boilers are included in this joint venture. Right now, we have around more than 2,000 employees working for this joint venture who does only supercritical boilers. And if you go to the next slide, you can see that our main head office is in Faridabad, where we have the marketing, engineering, and project management and supply management group sitting in Faridabad. And we have a manufacturing facility in Hazira, Surat. That is where we manufacture all our pressure pots. And you can see from in the last 10 years or 11 years, we have executed many projects. You can see the units starting from Rajpura, Chabra, Nigri, Malwa, Koradi, and Khargone. All these projects have been already commissioned and handed out to the customers. The units which are Tanda, Ghatampur, Buxar, and Kulja, they are under execution right now. And if you see this NTPC Khargone is the first USC unit which has been commissioned in India. That has been done by us. This is briefly about our company. And now I will come to the just for the unit ultra supercritical boilers introduction. I will just come to the next slide. This is, of course, everybody must be knowing in this audience, but just to refresh, I just have given a subcritical and supercritical, ultra supercritical definitions. You can see that the pressures of 16.7 megapascals is subcritical and temperatures of up to 560 degrees. Supercritical, it can go up to 593 degrees centigrade. When it comes to ultra supercritical, the pressures can increase from 24 megapascals to 31 megapascals, and the temperatures can go from 593 to 620. So this is the general, of course, there is no universal definition, but yeah, each country has different definitions. But in India, we are following these temperatures above 593. We are normally calling it as a ultra supercritical boilers. So this is the briefly about what is USC boilers and the trends. If you see in the supercritical units, you can see here. Actually, it's because since our partners are from Japan, I am giving the history of Japan, which they have started the supercritical boiler very early in 1968 with oil-fired boilers they have done, and then you can see from 1968. When it has come to coal-fired and then coal-fired going to the ultra supercritical, it happened in 1998. You can see that 1998 first unit of MHPS that has been commissioned, which is having ultra supercritical parameters of 600 and 600. After that, that has been increased a little bit to reheated temperatures up to 620. It has gone. So though it has gone to that level worldwide, India, we are now at 600 level. That is the first unit which we have supplied to Khargone. So that is ultra supercritical unit. But only change here is that pressures are not 24.5 megapascals. In Khargone, we are giving it 27 megapascals. So the pressure is a little bit higher. This is only just to show that again heat rate improvements, how it goes from a subcritical unit to the supercritical and supercritical to ultra supercritical, how it moves, it is shown. You can see here the latest project in India. I am showing that ultra supercritical we are at 600, but the pressure is little bit higher. That's why we have shown the star little bit upper side. So how the heat improvement takes place, that is shown in this particular slide. So you can see that from supercritical parameters of 566, 593, if you go to 600, approximately an heat rate improvement of 1.3%. Since we are increasing the pressure, maybe another 0.1% it will increase. It may go to 1.4 or 1.5 sometime. So it depends on the conditions. But that is how generally it varies from a supercritical to ultra supercritical when you go. Of course, if you are able to go up to 620 degrees in reheater, maybe you may get another 0.5% heat rate improvement more. And the next slide, you can just to have an idea, but of course there is no lot of assumptions in this particular slide, just to show that 700 megawatt with a subcritical, if you do and go to supercritical and then to ultra supercritical, how the improvements in the heat rate and then how much savings are going to happen in the coal consumption, how much ash generation reduction will happen, or how much CO2 and SOx will reduce. Just to show this academic interest, we have made a slide, we have prepared a slide. You can see it is almost from subcritical to ultra supercritical, it is around 5.5% improvement will be there in all the parameters, whether it is turbine heat rate or plant heat rate, coal consumptions, ash generation or CO2 and SOx everywhere, you are going to get that much of benefit. Then I just come to the ultra supercritical boilers which we have supplied. The features of that particular type of boiler I am going to show you. You can see our boiler has some unique features. This is ultra supercritical boiler which has been supplied to NTPC Khargone. We have a vertical water valve. Unlike it is a most of the OEM supply spiral valve for the supercritical boilers, but we have a vertical water valve with a rifle tube in the furnace, and we have of course we use high steam temperature for 600 class high temperature resistance materials, especially for the final superheater and final reheater. And then also the third unique feature is we have a twin fire vertex. It is not, we have two fireballs in the furnace. Unlike other this thing boilers, you have a single fire vertex, or you may have vent valve, air valve fired boilers, but we have a twin fire vertex of this thing furnace. It is a rectangular furnace wherein we have two fireballs within the furnace. And we use, though we have started this joint venture in 2009, that time there was no NOx requirements, especially in India. It was around maybe 760, 750 ppm or something like that is the requirement. But still, when we started supplying our boilers, we have supplied all our units with low NOx systems, including advanced pollution minimum burners, including a Mitsubishi advanced combustion technology, that is adding the additional air ports, or we call it sometimes SOFA. That is although our boilers are having this feature of low NOx burners as well as the SOFA burners on the above the burners. So this is the unique features of our particular ultra supercritical coal-fired boiler. And you can see in the plan the two fire vertexes, how it forms. You can see here from each mill, the 4 pipes will come, and then they are divided into 8 pipes. Each four pipes will form one fireball within the furnace. The furnace cross section is a rectangular cross section. You can see two fireballs, it happens. So with this, what will happen? You can see the low heat input per each burner, because the number of burners will be double. So that's why the heat input to the each individual burner will be less. So that's why the slagging and all slagging potential will be very less in the furnace. And final reheater temperature control, we control by second pass gas side dampers. We have a second pass with split pass. We have one superheater side and reheater side damper control is there. We control the reheat temperature with the dampers. Though we have a tilting mechanism, but tilting mechanism comes only after that. First, we operate with damper and control the reheat temperature without any spray. And if you are not able to do it, then only we come to tilting, but that is a secondary option. And of course, the superheater's temperature will be controlled by the spray. This is our basic features of our boiler. You can see in the general arrangement here, we have a secondary superheater in the main radiation zone. Final superheater will be at the nose portion. Secondary reheater will be on the horizontal pass. and then primary reheater on one side. As I said, second pass will have split pass, one side reheater, the other side superheater, and of course economizer will be there on both sides, on superheater side as well as the reheater side. This is the general configuration of our boiler. You can see, just I want to say that MHPS, when they introduce any new materials for high temperature applications, they do a lot of research. You can see that any new material, if you have to introduce, they do the factory test and then they will apply in the actual boiler test. Once it is succeeded, then only they will go for practical use. In some of the high alloy elements like code case 2328, HRC3 material, you see that factory test and actual boiler test have taken almost 10 years research. Then only they have applied those particular materials in the practical use. So this, just I want to say, just like that, a material which comes into the ASME code, they don't just apply into the high temperature application in the boiler. So they do a lot of research for the creep and fatigue this thing, and then only apply. Just I want to stress upon that. And these are some of the ultra supercritical boilers. These are some of the advanced materials we use, which is called, one is code case 2115, code case 2328. These are all 18 chrome arsenic material and 25 chrome arsenic material, and T92, E92 materials, and code case 2199, T23, depending on the requirement really. Of course, in Indian boilers, so far we have not used T23, but it is, our partners have experience of using T23 in the primary superheater and the primary reheater zones. This is where in the ultra supercritical boiler, what materials we use, just we are showing here. You can see that in the secondary superheater, final superheater, and final reheaters, most of the materials are stainless steel, code case 2115 or code case 2328. These are the materials we use, except for the inlet area, we use some T22 material, where the metal temperatures are less. Otherwise, all other material will be only stainless steel. And when I said high temperature resistant material, because we don't use T91, T92 materials, which is having high potential for steam oxidation. So we don't normally in the high temperature zones, we don't use in the gas path. Gas path, we don't use 91 and 92 materials. And of course, all other second pass, of course, we use T22, T12, and T10 grade A1. These are the materials we use. And of course, in the same this thing, we have presented in a different manner, each section, how we use different materials. Yeah. These are some of the, as I said, the burners which we use, low NOx burners, which we use, we call advanced pollution minimum burners. In the burner itself, we have a staging, 2-stage, this thing will, combustion will be there. So they have high ignitability and combustibility, high occupation rate of fire vertex in furnace, uniform heat flux distribution. Because we have a twin fire vertex in the furnace, across the furnace, it will be, heat flux will be uniform. And because of that, we achieve low NOx, low unburnt carbon, high efficiency, good operability, and low slagging tendency. As I said, since we have a twin fire vertex, number of burners are more, the slagging tendency will be less. This is again on on the burner front. You can main burners. Then we have above the main burners, we have additional air ports. So with this particular technology, we achieve the low NOx. I can tell you that our boilers, most of the boilers at 100% PM share, we achieve around 115 to 125 ppm. At low loads, maybe it will go maximum up to 150, 175 ppm at pot loads. So that is the sort of burners we have already supplied, and our boilers are operating in India. Then just I want to show from supercritical boiler to when we change to ultra supercritical, what are the changes which are going to come in the boiler basically. You can see here in the pressure parts, The final separator and final reheater surfaces will increase because the temperature we are increasing from 560, 593 to 600. The heat tubes and thickness will increase because the metal temperatures are going to increase. The thickness of the tubes we have to change for final separator and final reheater. Headers thickness and diameters will change. Of course, there is no material change from supercritical to ultra supercritical up to 600 degrees centigrade. But if you are going above 600 degrees centigrade, then we may have to use code case 2115, which is a 25 chrome stainless steel material. It depends on the metal temperatures which we calculate, but some of the portion we may have to use code case 2115. And some of the materials of pipes, because of the temperature increase, the material is changed from P91 to P92 in the headers and as well as the critical piping. And then because the temperatures are increasing, short peening of the stainless tubes have to be done for final separator and final reheater at outlet of the tubes. Only one end of the outlet we have to do the short peening. That depends on the metal temperatures. We have guidelines for those metal temperatures. Above that metal temperatures, we use the material with short peening of the tubes. When we buy the tubes, we buy with the short peening. And all other things like structures, non-press watt firing, nothing, no change will be there when you change from supercritical to ultra supercritical. Critical piping, of course, as I said, material will be changed from 91 to 92. Valves and all, casting material is not available for P92 equivalent, so we may have to use forgings for the valves. So there will be some increase in the cost. These are the basic changes which happens from supercritical to when you go for ultra supercritical boilers. This is again the same slide which I had shown that where the changes will happen. This is basically these things are going to happen in the final separator and final reheater. In the respective headers also there will be changes. So that is whatever I said in the earlier slide. Same thing has been represented in this particular thing. Only I said 2115 will be used only when the temperature crosses normally 610 degrees. In India, since we are not gone to 610 level, at least in Khargone, we have not used code case 2115, which was not necessitated. So we could not, we have not used this particular material. Of course, P92 we have used for all the headers and as well as the critical piping, which has been changed from P91 to P92. That is briefly about this ultra supercritical boilers, supercritical to ultra supercritical. What are the changes going to happen? I'll just show some of our experiences in ultra supercritical boilers. Our partners MHPS Japan, they have experience. You can see that Mushimi unit, which has been commissioned in 98, which is operating at 607, 605 at boiler outlet temperatures of mainstream and reheat. There are other units, Maizuru, Hirano, Linko. These are all Japanese units. They have Japanese direct MHPS has supplied units, which are all with ultra supercritical parameters. And they have supplied through the licensor in China with the same MHPS technology. There are maybe more than 20 units which are operating in China with the same temperatures of 600 they are having. When it comes to India, we have done our L&T MHPS boiler. We have done NTPC Khargone is the first project of ultra supercritical which has been commissioned recently. January 2020, first boiler has been declared COD, and the second boiler has been declared COD in April 2020. And now we got latest orders, 2 orders from SGUNL Buxar and TSDC Kurja. These are also ultra supercritical boilers which are under execution now. This we got only maybe 1 year back. These orders we got it. These are under execution.
Mr. Chidara, I think I request you to close it in 2-3 minutes.
Yeah, it's over. That's right. I will be closing in 1-2 minutes. Yes.
Thank you.
Yeah. This is the Khargone ultra supercritical boiler which has been supplied by us. You can see that customer is NTPC Khargone and commercial operation first unit 1-2020 and 4-2020 is unit 2 we have commissioned, completed COD. And the steam conditions here, you can see 27.2 megapascals and temperature 603, 603. Fuel is, of course, Indian coal. And the same thing, you can see here, that same project, you can see that it is a boiler type, is once through ultra supercritical sliding pressure vertical valve, 2-pass design, firing system 2.5 pin fire vertex, 8-corner low NOx burners. Steam conditions, I have already told that 27.26 megapascals with a 603, 603. Fuel is Indian coal with a GCV of 3,400, ash of 43%. And as a starter fuel, LDO is there, and you can see the COD of those two units which are operating. And we have, for your information, we have successfully completed the PG test of first unit some 2 months back, and we got the acceptance certificate also from NTPC. With this, I am closing my presentation. Thank you very much. If you have any questions, you can always ask in chat box. I will reply. Thank you very much, Mr. Agarwal.
Sir, you are on mute.
Thank you, Mr. Chinao, and I really appreciate for sharing the experience in this area. Now I request Mr. V. Tanwani from AGM from NTPC, and Mr. Sagar Luthra and Mr. Abhishek Siani assisting him. The paper is on India's first supercritical thermal power plant, Khargone. So I invite Mr. Tanwani and his team to make his presentation. Thank you. Mr. Tanwani.
Yes, sir. Thank you, Agarwal sir, for giving this opportunity. We welcome all the participants to India's first ultra supercritical power plant, that is Khargone. In next few minutes, we'll be covering project synopsis. Then we'll be discussing the key design features, and lastly, we will be taking key operational features and issues. Myself, Mukesh Kumar Burma, along with my team members Sagar Luthra, Abhishek Sani, and our HOD, Sri Vijay Tanwani sir. We will be taking over this slide to the presentations. Khargone being the first ultra supercritical power plant, because we will be operating at the pressure of 270 kg per square centimeter, the temperature of 600 degrees Celsius. We will be having a unit efficiency of 41.5%. This has led to a specific coal consumption of 2.6 with the 3.3% CO2 emission reduction. This makes us the highest efficiency power plant in the India. The project is located in the Khargone district with the capacity of 1320 megawatt. The whole project is spread over 1,765 acre land. We'll be requiring around 40 MCM per annum water, and the coal is being transported by the Indian Railways. Will be requiring around 6.5 metric ton per annum. With that, we have a take-up of 37 kilometers away from the plant. The estimated cost of project is 10,876 crore. The power has been allocated to 7 beneficiaries, with MP is the biggest share. It has 50% share. Then come to Gujarat, next is Chhattisgarh, and then Maharashtra. Current our share is 2.58 rupees per unit. Coming to commissioning timeline. For unit 1, we have done video on 29 December 2019. Within the span of 180 days, we have synchronized the unit on 27 June 2019. Then we achieved a full load on 38 August 2019. The unit has been declared commercial on the 1st February 2020. This whatever learning we made in Unit 1, we applied in Unit 2, that have given a result in terms of reduction of the timelines. As far as Unit 2 is concerned, we have done BLU on 21st November 2019. Within the span of 40 days, we have a synchronized unit on coal on 31st December 2019. And within the span of 59 days from BLU, we have achieved a full load on 19th July 2020. And the unit has been on commercial operation post April 4th April 2020. Coming to key design features, we will be operating ultra-supercritical parameters, 270 pressures and 600-degree temperatures with a unit heater of 2070. As far as boiler design feature is concerned, Mr. Rao has covered all, but especially mentioned we have twin firewalls with the combination of rifle and plain tubes and low NOx burners. As far as turbine is concerned, we have all reaction stages to meet the peak load, the 105 unit load. We have been provided to all load walls. The LPT last stages has been integral route, and we have fuel pressure condensers that has substantially increased the efficiency. Also, we have a duplex secure at the condenser rate because last two extension have been and the very low pressure that has led to both the heater has been enclosed in the single shed. Next, we have installing the FGT. The technology has been provided by the Chiudo Corporation. The technology is known as jet bubbling technology. We have SP with the particulate emission level of less than 17 microgram per normal meter cube. We have a 400 kV GIS with 15 bays, and this is the compact layout as well. There is no separate zero liquid discharge system. This has been incorporated built in the system. We have a ETP system, coal slurry settling plant, AWRS and STP. All these provide, this will enable us to zero liquid discharge. We will, as I said, that we are taking water from the Nabha river that is 42 kilometers away from the plant site. We have installed GRP pipelines with the size of 900 mm and 700 mm. Also, our township also is a smart township with the IT infrastructure covered to home services that also incorporating solar energy, smart energy and water management system, and security and survey systems. Next part, the key operational features will be taken over our colleague Sagal Luthra.
Good afternoon, friends. So, the certain key operational features of this particular boiler is that we're able to achieve the design parameters of 603 degrees Celsius even at the part load. Next thing is the in the tri-sector RAPH which has been provided, the technology used is such that the gap between the sector plate and the seal is adjustable, which help us to maintain the cold end temperature of 116 degrees Celsius and almost 5% inbuilt air leakages. The 8-corner firing system helps in better combustion. We can say that even the last 1 year of operation, we haven't faced even a single MFT or flame failure with the first coal of 2900 CCV. The radiator spray has been minimized to almost zero by using GD dampers, and the temperature mismatch of the left and right in superheater or reheater is almost nil. The one thing which I want to talk about is that there is a very smooth transition from dry to wet zone or from wet to dry zone without any metal temperature excursion. Since the quantity of feed water required for initial startup is almost very low, 420 tons per hour, so we can actually make a startup in a very less time and with 1 MTBFP of 30% capacity only. The DP across the water wall is almost negligible. That helps us in saving a lot of power in boiler feed pump. And since during the soaking, during the startup of a turbine, the soaking speed is at 2300 rpm. So this has led us to a better heating, a more uniform heating of the turbine. So that helps us in achieving better parameters heat up of turbine and reducing the stress level in the turbine. Next thing I want to talk about is the vacuum deaeration of deaerator. That helps us to achieve the DO, dissolved oxygen, of less than 5 ppb. And since the deaerator outlet vent is directly connected to the condenser, so the water loss through the deaerator is almost zero. Well, water loss which through the vent of the deaerator is actually being utilized in the condenser. So next thing which I want to take about is what are the key issues which we are facing actually in the operation of this ultra supercritical boiler. That would be covered up by my counterpart Abhishek Sen.
Thank you, sir. So, apart from all the good things, we have some issues also. Yes, the cleanup cycle takes approximately 45 hours during cold startup time. This is basically because of supercritical nature of this power plant. We do need exceptionally good water quality in order to ensure good life of the boiler. So the cleanup cycle takes 45 hours, and this results into oil consumption of around 450 to 500 kL per cold startup. There is no provision of wind box tamper control after 30% load. We don't have any control as in the operator hand. No provision of biasing in feed water. The loop of operator is provided here. Actually, sometimes the temperature may go out of hands, and there is no provision for biasing in feed water loop, which might have been helpful. During low loads, it is difficult to get differential pressure for superheater spray flow because the superheater spray flow is taken from the eco inlet itself. Since at low loads, the pressure is low in eco itself, so the spray pressure is very less. Due to frequent ramp up and ramp down, the secondary bypass valve gets stuck up, probably due to high pressure. Ash accumulation in flue gas duct after APH is an issue here, and guidelines are installed here to rectify this issue. And yes, some progress has been made. During operation of OLVs, abdominal sound is being generated. No provision of seal steam pressure control in TDPFEs is there. Actually, during low loads and during high loads, the seal steam pressure, we can't control the seal steam pressure in the TDPFEs. This has led to some water moisture inside the TDPFEs. MDFP scoop auto tracking feature is also not available here. As whenever a TDPFP goes out, we have to load up the MDFP, and this has to be done manually. There is no auto scoop tracking feature available here. So these are some key issues, and apart from this, during ramp up and ramp down, the temperatures do vary a lot, and we have to control them manually. Probably due to all the auto loops are not tuned properly. So these are the key features, the key issues I discussed. Thank you all for listening to us patiently, and we'll be open for the questions later on, I guess. Thank you.
Sir, you are on mute.
Sorry. Thank you, Tanmay and team, and it's a good analysis you have given about the new unit which has been commissioned, and we will take up the question answers at the end of the session. So I think we'll move to the next presentation, and that is by Mr. Rajesh Kumar. He is head operations from Nabha. Mr. Rajesh Kumar is having about 30 years experience in project management, and I invite him to present on the best O&M practices for supercritical plants. Mr. Rajesh Kumar.
A very good afternoon to all the members in the distinguished panel, my fellow speakers and members in the audience connected online. I thank the organizing members for giving me the opportunity to participate as a speaker in this prestigious Power Plant Summit. This summit provides an immense opportunity to all the power plant professionals to join together and share their thoughts and views for mutual benefits. I am Rajesh Kumar and I represent Nabha Power Limited as Head of Operations of the plant. I shall run through the presentation on some of the best O&M practices that we have implemented in 6 years of operation on the plant. Everybody can see this?
I think you have to enlarge it.
Just a minute. You see, sir, now?
Not yet, sir.
Just.
Could you try resharing your screen?
Yeah.
It's visible now.
Okay, thank you. So it is Nabha Power is a 2 into 700 megawatt supercritical thermal power plant located at Rajpura in Punjab. I'll briefly run through the company profile. It is a It is having 25-year PPA with PSPCL. Sorry. And having a coal linkage with SECL. All the major equipments manufactured indigenously through technological tie-up with MHPS of Japan, state-of-the-art manufacturing at Hajira. Our plant contributes 50% during the non-peak seasons of Punjab requirements and 25% during the off-peak seasons. We are the top in the merit order of Punjab. And we are most reliable. Like consistently, we had availability more than 85% in last 5 years. We are one of the highest efficient plants, having a designed heat rate of 2205 kilocalories per kilowatt hour. We are environmentally friendly, advanced PM burners with having zero liquid discharge. This is the performance indicators of the last 5 years. You can consistently see that our availability has been higher than 85%. That is the normative PL availability. Consistently, it has been since first year only it was 91%, and after that also it has been above 85%. Our heat rate is also very close to the design. Last year we closed the year with 2281 kilocalories. Our internal target to allow for the partial load operation was 2295. So we achieved better than the target last year also. Our all O&M best practices are driven by on 3 pillars, that is the safety, reliability, and sustainability in this order. Our reliability is taken care by efficient and economical operations of the plant. Of course, this is propped up with the monitoring and optimization, and sustainability is through economical and clean generation of the power through effective control and review and monitoring of the systems. We have gradually switched over to reliability centered maintenance after 6 years of operation, and we are on the path of journey. We started with preventive maintenance, that is the corrective maintenance also, and preventive plus combination of corrective, predictive, as gradually we switched over to preventive maintenance, corrective maintenance, and a combination of predictive as well as proactive maintenance. Then we have switched over to reliability centered maintenance. In future, we can go to risk evaluation and prioritization system. In reliability center of maintenance, we have lowered the cost with high availability also. So it is an optimal mix of maintenance cost as well as availability. As coal is in shortage during peak season of this plant, so we are firing different types of coals from wherever sources we are getting, whether it is imported as allowed by PSPCL or through different sources as given by SCCL. So last year we fired mix of imported and domestic coal with GCV ranging from 3,300 to 5,700 kilocalories, including Indonesian coal with high VM and high moisture. The moisture content was from 11% to around 20 to 22%. This simultaneous firing of 4 different type of coal without any incident was a great achievement. We achieved with a very minimal metal temperature excursion or any adverse impact on combustion without deviating from the design limit. This we achieved through development of in-house automated tool for shift-wise temperature monitoring by the shift personnel, and of course on daily basis it was monitored by the senior management team. We developed a special procedure for developing for firing the Indonesian coal of high moisture with high VM to avoid any chance of mill explosion. Of course, we closed the year without any incident. Simultaneous firing of 4 different types of coals without any incident of metal temperature excursion or adverse impact on combustion. As our previous participants have also talked that unit cold startup for a supercritical power plant is a lengthy process. It requires that the water entering through the boiler before light up has to be ultra pure. So initially when we started, our total startup time from condenser vacuum pulling to the synchronization was around 36 hours. Gradually, with every startup, review of every startup, with optimization of every startup by reviewing the startup process, the startup curves, and whatever the problems have been faced, we have reduced it and optimized it to 24 hours. This partially we have done because the requirement is such that before the water is entered into the boiler, the DO level should be less than 10 ppb and iron should be less than 100 ppb. So removing DO was taking a lot of time. So we in-house developed a procedure where we raised the deaerator pressure and temperature for faster removal of oxygen, resulting in faster LP cleanup. Because as the temperature was raised, we strike the point for the deaerator pressure where the temperature could be removed faster. Once our plant is stabilized, then we switched over from HFO to LDO. Of course, some of the states, they have banned use of HFO, but we did not have that requirement in this state. But since our plant is stabilized, we thought that and the number of startups were reduced gradually, we thought it is better to switch over to LDO without much change in the design. And all 24 guns are run now on LDO. HFO pump has been replaced with LDO pump. Upper elevation are kept with steam automation, and LDO is stabilized with fast, leading to quicker pressurization of boiler. An unwanted requirement of keeping the HFO in flowable mode by keeping the steam charged has been avoided, and we are saving on heat rate in that. These are some of the best practices in water management, water and energy management system. Our DN cycle makeup has been reduced from 0.67% in the base year to 0.37%. Last year it was 0.37% by extensive monitoring, by shift-wise monitoring, as well as online measurements through thermocouples on some high energy drain valves. Some of the high energy drain valves connected in the interconnecting pipes of the main stream line and reheater lines or CRH lines, they are prone to passing because they are subjected to high pressure and temperature. So we have we have put up thermocouples downstream of the valves, and we are monitoring the temperature. If it is going higher, then we take corrective action as and when the opportunity arises. In ash handling plant, all the seal water is harnessed into clarifier for ash water recovery. This has resulted in huge saving of around 3,000 metric ton of raw water per day. So this much of raw water drawal has been reduced. We have switched over from drawdown mode from shift-wise to a daily basis. And on each day, we are doing our bottom ash drawdown to check the flame intensity or if there is any clinker formation or not. So that we are checking on daily basis. On energy management system, we have installed steam traps in drain lines of pre-warming lines of LP war. This has resulted in investment. This has caused an investment of 7.1 million and resulted at saving of 3 kilocalories and within a payback, and the payback was 3 months. NDCT makeup has been done through gravity because our line which was coming from HRSCC, it was going up and then entering the clarified water tank. We have taken a T off from there, and through gravity we are making it make up to the CW system. So CT makeup pump running has been completely avoided. The investment, whatever was done, the payback was 1.2 years. HFO pump, which is HFO or rather LDO pumps, which is right now we are using it as, it was during the boiler operation, it was supposed to run continuously, and unnecessarily it was running at full pressure. So we have done, we have installed a VFD, and we are saving it because it has to maintain a low flow and pressure only. We have replaced 2 number of WDC valves. In a supercritical boiler, these WDC valves, which are high pressure valves, which are directly connected to the condenser, and one side it is connected to WSDT drain at 265 bar. So there is every likelihood that there is a passing of these valves and heat is getting lost to the condenser. So we have done the design change, and with and whatever modification has been done after removing the internals and changing the internal, the payback is 1 month only. We have switched over to oxygenated treatment because it gives increased focus on boiler water treatment. Coordinated water treatment or oxygenated treatment, as it is called, it is better for reliability and efficiency. The magnetite layer changes over to hematite layer, which is very smooth. There are not serrations, and pressure drop across the tubes get reduced. Like on the right side of the slide, you can see the curve where in AVT mode, the boiler pressure drop is higher, and in CWT mode, with the passage of time, the rise of the DP is very less. It is constant almost. Effective monitoring has been achieved through online monitoring, online measurements, that is maintaining optimum DO at the boiler inlet, at the economizer inlet, and in the condensate circuit with online DO analyzer as well as ORP measurements. We have installed metallar Teledo make chloride analyzers, which has accuracy less than 1 ppb, because chloride is very, very essential for the at a high pressure and temperature for the boiler, for the turbine. We are getting yearly deposit analysis at reputed lab externally. So in a nutshell, healthiness of SWAS is the key for a supercritical boiler. We have developed a state-of-the-art coal lab. Through laboratory information management system, the samples are collected through auto samplers and it is randomly coded. The entire system does not require any manual intervention, so that the chances of human error or any other error or mistake is totally avoided. The rake registration is done, the barcode is generated and on random basis, and each sample is barcoded. So the entire cycle, when the testing of the coal is done, nobody knows which sample is there, because since we are a load center plant and we are getting coal from different sources through SACL, through imports, or through different places of CIL, through multiple sources, it is very important. And since it is being transported from 1500 kilometers, it has a high financial implication if there is a slight error in measurement of GCV. So this LIMS integrates the GCV, proximate and moisture, and delivers the final results. Our coal lab is NABL certified. It has all the modern facilities, highly experienced team is there. And the LIMS, as I told, there is no manual intervention, complete process is automated and without any tamper. It is totally tamper proof. As you all know, power sector is very vibrant nowadays, and it requires a lot of challenges, lot of monitoring, effective monitoring at multiple levels because of integration of renewable energy, flexibilization, etc. So we have at Nabha Power, we have taken a lot of initiatives for digitalization. We have developed a operator training simulator, where the virtual method, it is a virtual method to provide training to new operation engineers. It has simulated a startup shutdown. It simulates the process transitions and changes, and all abnormalities, runbacks can be built into. It is a Protex-made software where all these engineers can run the different, can simulate the different situations and run and learn the thing. We have a very effective vibration monitoring system where all the data is collected at make software, which fetches the data, real-time data from all the critical drives, turbine and fans, mills, etc. And it analyzes all that through FFT analyzers, through orbit analyzing, and finally gives the input for maintenance engineer, for our technical services team to do further course analysis. This is a very, very effective tool. We have a maintenance management system at Maximo, which we have put it on mobile also. So it is available to all the senior people on the go. Work can be seen remotely from anywhere. It can be secured accessibly. Approvals can be done on mobile, so that faster decision making is done. We have also developed a module in Maximo for HSE, where hazard identification, risk assessment can be done. Incident reporting and risk investigation can be done on module of the Maximo. And safety instructions and even regulatory compliances are built into it. And all senior persons can see on the mobile which compliance or which licenses are about to expire, so that corrective action can be taken in time. We have developed extensive mobility, like around more than 300 critical and vital parameters of the plant are available to all senior persons or key persons of the plant, and on the run, they can see all the parameters for any faster decision making, like they need not call the control room anytime for any parameters. Like I, as an operation head, am able to monitor sitting at around 35 kilometers from the plant on real-time basis, and any time, any odd hours, or even if I'm on tour, I can monitor all the parameters. So that unnecessary call to the control room can be avoided. If I think requirement is there, then I call, but otherwise I am able to see all the parameters. It has a refresh time of 30 seconds. Every 30 seconds, the data are refreshed. On mobility, we have taken PRPO approval also on mobile, so that all the requisite HODs or section in charges, they can approve the PR and PO, and they can release the same. Statutory compliances, I talked that alert is generated once it is about to expire, and integrated email is also generated. This is also another effective tool in modern day where there is a lot of thrust on digitalization. We have developed an energy management system, and all these data are available. Sorry. All these data are available through a platform, and it triggers any parameters which is going any critical drive or anything which is consuming higher energy. Then it immediately triggers alarms on the very next day, and auto email is generated to all key persons, all stakeholders, for taking corrective actions.
Sir, I think we have to close in next 1 or 2 minutes.
Okay, sir. This was a light slide. Thank you, sir. Thank you so much.
Thank you.
I would be taking all the questions in the last, if any. Thank you, sir.
Thank you for providing us the insight of the Nabha, and Nabha is definitely performing very well. And I think we switch over to the next that Mr. Angelos Pukinos. He's Assistant Deputy Secretary, Clean Coal and Carbon Management Office of Fossil Energy, US Department of Energy. He is having about 40 years of experience in fossil fuel area. So I invite him to present on Coal First Initiative, Resilient, Small, Transformative. Mr. Angelos Cook.
Thank you very much. It is a pleasure to be with you this afternoon, your time, this morning, my time. It is always a pleasure. It's also a pleasure to see the significant progress that you all have made in the application of supercritical systems, coal-fired systems, to your grid. I recall about 8 or 9 years ago visiting the NTPC R&D and training site outside of Delhi, and witnessing the engineers being trained in the first supercritical power plant, how to operate the first supercritical power plant that NTPC was getting ready to put in line. So again, it's a great pleasure to be with you, and thank you for allowing me to speak about our program. Scott, if you could go to the next slide, please. I want to make sure that I mention to you that we have just completed a United States-India Strategic Energy Partnership Program, where we have initiated a dialogue between Indian government ministries and companies and academic research organizations to look at R&D priorities and secure funding for R&D programs, advanced R&D programs in the area of coal, and also a possible demonstration. Why are we still looking at coal? There are two inevitable things that have been happening currently. One is that renewable energy will continue to increase its market share in electric generation. However, coal, as you are demonstrating, will continue to play a vital role in providing low-cost, reliable, and most importantly, resilient energy for the foreseeable future. The R&D that we have commissioned does not only cover extending operating lives of the existing plants, but also improving their performance and developing the next generation coal plant that would meet, as I mentioned before, the changing needs of the electric sector. And some of the previous speakers touched upon some of the requirements that you see in your everyday lives of and tasks of providing this reliable electricity. So as a result of that, our coal program is committed to creating a more nimble or flexible new generation systems that are smaller in size to allow them to load follow the inevitable application of intermittent renewable energy. And we're also committed in doing this, ensuring that this next generation of coal-fired systems provide the cleanest and hence carbon neutral and most efficient way possible in their application here in the United States, but also in the world. Next slide, please. What do we hear from people that we talk to that are stakeholders in our R&D program? One, that coal must play and will continue to play a role in future energy systems. Two, that there has to be a improvement in base loaded plant efficiency for both the new and existing generation, such that they make the coal generation more competitive, commercially competitive, and at the same time eliminate air pollution, including being carbon neutral. As you have noted, capacity factors, at least in the United States, have dropped to the levels of 50%, requiring that these plants spend increasing time in cycling mode, therefore requiring that we address reliability and lower efficiency and the shortening of the expected plant life. Long term, we need to include carbon capture, utilization, and storage so we can achieve carbon neutral levels. And that means we have to reduce the cost of carbon capture. And last but not least, we need to find, as coal generation and consumption is reduced due to the renewable markets, we need to find new markets for coal such that we can keep people that dependent on coal gainfully employed. Next slide, please. We have, as I mentioned, 5 major areas of focus in our program. One is the Coal First initiative, first standing for flexible, innovative, resilient, small, and transformative. Carbon capture, utilization, and storage, coal to products, hydrogen production from fossil fuels, including coal, for power generation, for its use for power generation and transportation. And last but not least, looking at creating new advanced power cycles using things like supercritical CO2 as the working fluid, both in a direct and indirect manner. Next slide, please. Let me talk about Coal First. Coal First, as I mentioned, stands for flexible, transformative, innovative, small, resilient plant. And by flexible, we mean that it has to have high turndown rates, high ramp rates, and shorter startup times. It also has to be highly efficient and more efficient than the current state-of-the-art advanced ultra supercritical systems. It also has to have zero or near zero, including net negative CO2 emissions when you co-fire coal with biomass. It is the only power plant R&D effort in the world as we know it that is trying to achieve this type of plant, this type of levels. We also wanted to be flexible in terms of, if possible, produce power and or hydrogen for polygeneration, either hydrogen for power or hydrogen for chemical production. Next slide, please. Why are we looking at hydrogen? A lot of countries, ourselves, our country included, are looking at possibly transforming into a hydrogen economy. As you see the CO2 emissions, it's interesting to note that transportation now has surpassed power generation and industrial energy generation in terms of CO2 emissions. And hydrogen allows for having a transportation sector that is CO2 free, but also other criteria pollutant free, such as hydrocarbons, particulates, and NOx. Hydrogen can be produced from fossil fuels. And if you go to the next slide, and it can be produced at significantly lower cost than what it can be produced through the process of electrolysis, including when the source of electrical power is the so-called free renewable power sources such as wind and solar. As you can see from this slide, hydrogen produced through coal gasification with carbon capture, CO2 capture and storage system can be produced up to $2 per kilogram. Hydrogen produced from steam methane reforming from natural gas can be with carbon capture, CO2 capture and storage can be produced for approximately $2.50 per kilogram. We in the United States have done a significant amount of research in using hydrogen for power production, and we have developed combustion turbines that run on hydrogen, and we intend to continue working on advancing this type of technology. Next slide, please. I mentioned that hydrogen can be produced through fossil fuels, and indeed that is the case when you look at the world production of hydrogen. The world production of hydrogen, approximately 70 to 75% of hydrogen is produced through steam methane reforming, where about 20% is produced through gasification of coal, with the rest of it being through electrolysis. And the reason for electrolysis being so low is simply economics. The cost of electrolysis needs to be reduced by 75 to 90% in order for it to be competitive. Therefore, coal and fossil fuels are very critical in the production of hydrogen. Next slide, please. In the Coal First initiative, we are looking at one of the programs that we're looking at is the what we call polygeneration, which is basically a system that produces power while at the same time it can be produced hydrogen that can be used either as an energy storage system or as a power generation source. And all of that needs to be done with CO2 capture. Next slide, please. On the Coal First program, we have completed several pre-FEED studies, front-end engineering and development studies, looking at, among other things, a pressurized fluidized bed combustion system with supercritical steam conditions, an advanced ultra supercritical small flexible power plant that uses pulverized coal as the feed system. We looked at the supercritical indirect and direct power generation cycle, and we also looked at a system where we had a ultra supercritical boiler in combination with a natural gas turbine. As a result of all these pre-FEED studies, we are now in the process of requesting proposals for full FEED studies. And if you can go to the next slide, for 4 technologies. These full FEED studies would be for a power plant size of 50 to 350 megawatts. And the 4 technologies that we're looking at is 1, small, modular, flexible, advanced, ultra supercritical coal-fired power plant. Now, second one is pressurized fluid bed combustion with supercritical steam cycle. Third one, a hybrid natural gas turbine, just normal supercritical coal-fired boiler power plant. And last, a gasification of coal and biomass to generate electric power and carbon-free oxygen byproduct. All of these with carbon CO2 capture and utilization system. I want to go back a little bit on some and be very specific on some of the requirements. These systems will require to have a 5-to-1 turndown. In other words, they should be able to operate it down to 20% capacity without any support fuel. 2, they need to have less than 8 hours startup time. And 3, they need to have 4 to 5% of MCR per minute rump rate. So these are some of the requirements that we are looking at. The small modular flexible advanced ultra supercritical coal-fired plant, we're looking at 300 bar operating pressure and steam temperatures, reheat and superheat, in the 650 to 710 plus degrees centigrade with single or double reheat. So this would give you an idea of the areas that we're looking at. If you can go to the next slide, please. This is just a process flow diagram of the flexible gasification power with hydrogen and chemical production system. And if you go to the next slide, I would like to mention this.
I
Yes,
think we have to close in next 2 minutes.
my summary slide. So we will do that. Thank you. These technologies require advances that we have achieved and we are continue to improve in several areas. For example, in materials, it requires advances to materials that can withstand the steam conditions that I just outlined. As a result of that, we have helped sponsor the development of Inconel 740 and Haynes 282 materials. It requires improvements in water management and condenser efficiency. It requires advanced sensor and control systems that not only optimize power plant performance, but is able to predict condition-based maintenance or predict failure. And last but not least, advances in advanced combustion, such as 100% hydrogen combustion turbines, and of course, gasification. Next slide, please. And with that, I would like to thank you all for being so patient and listening to me and for allowing me to participate in your workshop. Thank you.
Thank you, Angelus and Mr. Scott Smalls, for giving insight about the new initiatives being taken for utilizing coal and competing with the environment conditions to meet all those type of requirements. And I'm sure those type of requirements will be needed in the near future for because of the so many boundary conditions of the environment norms. All the success. I think we have come to the end of the session, and all the papers, all the 4 presentations were very interesting and covering the new. Some of the papers covers are the new units which are commissioned recently in India, and they are very efficient in terms of the heat rate, and the designs are also unique in many respects. And I'm sure they will be they are going to be the leading and maybe many states will be running these units as a base operating stations because of their performance. And I think the O&M practices adopted by Nabha are also giving very good fruitful results. So many of the utilities will be benefited with the type of information shared in this session. So I thank all the speakers to spare their time and cover their experience, sharing their experiences. Many utilities will be benefited with that. So thank you once again, and thank you, Swapnil, to help me in conducting this and so smoothly. So, Mr.
Sir, we have a couple of questions from participants. So if you allow, we can ask them.
Yeah, definitely. If you can check what are the questions there.
Yes. Sir, I'll read it out. So we have 3-4 minutes before closing it. So we have a lot of questions, but I'll be asking more important ones.
Yeah.
So this question is to Mr. Rajesh. What is WDC? Why replace WDC valve? And second is, what is drawdown method?
Yeah, WDC valve is water separator drain control valve, which is what happens during a startup. This supercritical boiler has to act as a subcritical boiler unless it transits to supercritical zone. So that time the water has to circulate and the water has to be brought back to condenser, and then again it is to be circulated. So what happens, this valve is one side having a pressure of that water separator drain, which is during full load operation, it is around 260 plus bar pressure, and the other side is connected to condenser. So since this valve is subjected to such a high differential pressure, there is every likelihood that it will be passing. So there was a problem with the design. It was a wedge type valve, which was a parallel slide valve, which we have replaced the internals with a wedge type valves. And now we are having a good result. There is no passing as such.
Okay. Sir, what is drawdown method?
Pardon?
Sir, what is a drawdown method?
Could you please elaborate?
Sir, in one of your slide, it was mentioned drawdown method.
Yeah, drawdown method for the bottom ash. Right. Yes. What happens once in a day, we completely drain out the bottom ash from the bottom hopper. Bottom ash water. The bottom ash is water impounded, and complete water is drained to check that all these clinkers, whatever minor clinkers or minor ashes which is getting formed, it is falling vertically, and there is no clinker as such in those portions, large clinker. Because a clinker, if it forms, it can be dangerous for the operation. So once in a day, we check that.
Thank you very much for answering both the questions, sir. Second is, sir, to NTPC Khargone, what is a dual pressure condenser?
So a dual pressure condenser is basically both condenser operating at a different pressure. We have a cooling water flow in a series. So cooling water flow first pass through the LP condenser. It will be a lower pressure, and then same cooling water flow passes through the HP condenser. It will be higher pressure. So both condenser having a different pressure.
Okay, thank you.
But average is lower.
Okay, sir. Sir, one more question is to Mr. Kotagiri. Kindly explain a second pass arrangement of L&T boilers.
Yeah, I think the second pass is divided into two pass again. You can see you have a division wall in between, within the second pass. One side, the left hand side, the reheater will be located, and right hand side, the superheater will be located. That is the primary superheater and primary reheaters. Below that, both economizer will be located. So to control the reheat temperature at the bottom of the economizer, you have a dampers. So whenever you require a more reheat temperature, for example, you will allow the damper to open on the reheater side. So the more gas flow will go into the reheater side and temperature will increase. And superheater side, the damper will close. Again, when you require lesser temperature, then superheater side damper will open and reheater side little bit close. So that is how we control the reheat temperature. So that's why, as you can see from the NTPC presentation also in the Khargone, without any spray, you will be able to control the temperature and you will reach that 603 degrees. So that is how it is. I think I could clarify.
Thank you very much, sir. Sir, last question to Mr. Rajesh.
I have one question with Mr. Chinna now.
Yes, yes, sir.
Mr. Chinna, now I just want to know regarding the balancing of the coal flow from the mills to the boiler. Do you think that you need use of dirty pitot so that periodically it can be checked and uniform flow on all the pipes can be maintained?
To answer your question, sir, actually when we do the calculation of this flow balancing, accordingly we provide normally fixed orifices with ceramic lining we provide. So what our earlier units, whatever we have provided, there we have not provided any dirty pitot tubes to measure the velocity of this thing and all, and they are all working well. But of course, in NTPC, normally they insist for dirty pitot tubes and variable orifices. So we have been going, recent units, we have been giving a dirty pitot tube. With the dirty pitot tube, they will see the velocities. If they observe any unbalance, they will adjust in the orifice. Because it's a variable orifice, they adjust the flow and bring back to the plus or minus 5%. That is how they do it.
But then if the orifice can be replaced also, but can this be used in the previous units also?
Which orifice you are talking about?
The orifices in the coal pipe during the overhauling time, they can be replaced depending upon if there is a disbalance. But then can they use dirty pitot as a practice for doing coal balancing?
Yeah, you can do it, but once you give the fixed orifice, so unless an annual overhaul comes, you cannot do anything because it's a fixed orifice, you cannot adjust. By seeing the dirty pitot tube also, you cannot really do anything. So you have to wait till the overhaul. But if it is a variable orifice, you can still do the little bit adjustment in the orifice. That is possible.
Okay.
Sir, last question to Mr. Rajesh. Are there temperature exertions to more than 55 degrees Celsius at CEP outlet during initial cleanup?
No, there are no.
Okay.
It could be minor excursion could be there once or twice, but not much.
Okay. Thank you all panelists for answering the questions. Sir, sir, I request you to please close the session. Just a small announcement. Next session will be starting in few minutes. So request you to have a health break of 5 minutes and please join us for next session. Request session chair to please close the session.
Thank you. Thank you. Thank you, sir.
Thank you, everybody. And
Thank you for Agrawal sir. Thank you.
Thank you.
thank you. Thank you for sparing your valuable time.
Thank you.